In this lesson, we shall look at physics. We begin by looking at interference, Young's double slit experiment. Now, there is a light source, right? A single light source, and this is the schematic representation of double slit interference. A single light source, such that now the light spreads and therefore gets into two slits. This is monochromatic light from an illuminated light falls on slits S1 and S2. So this is monochromatic light. Therefore falls on the two, so on the illuminated slits S1 and S2. The sets of waves spreading from these slits are identical since they're both derived from the same original source, that is the illuminated source. So these are identical. Right, interference fringes are observed on the screen in the region of overlap between these two sets of waves. Right, you can see an overlapping region there. As obviously these sets of waves spreading from these leads are themselves identical, they overlap there, creating what we call an interference fringe. Right, we'll just go through this quickly and then we will go through the tutorial questions. Right, notice that the interference fringes could be observed, right, in any plane in the overlapping region. Now, these fringes are therefore said to be non-localized. Compare this with the thin film interference fringes discussed in section 5.2. But you notice that the interference fringes could be observed, right, in any plane, could be observed in any plane in the overlapping region. Because they could be observed in any plane in the overlapping region, we say these fringes themselves are therefore non-localized. Non-localized. Compare this with the thin film interference fringes discussed in section 5.2. Right, figure 8. Geometry of the nth bright fringe at P. A distance x from the plane of the slits S1 and S2 separated by distance d. Right, so you have that. So in figure 8, d is the separation of the sources. So the sources have a separation distance d. And yn the distance from the axis to the nth bright fringe. P on the screen. Okay, there's yn there. Now suppose Q is a point such that S1P is equal to QP, right? So we're looking at S1P is actually equal to QP, right? Then if you then say, you take S2, if these are equal, yeah, these are equal, S1P is equal to QP, then if you take S2P is bigger because there's a little gap here. So because of that, then if you take S2P minus S1P, then it's going to become the difference, which is S2Q. Constructive interference, that is the bright fringe occurs. When does the bright fringe occur? Right, the bright fringe occurs when the S2P minus S1P is equal to n lambda. Hence, obviously, we then say that SQP itself is equal to n lambda. Because why is it that S2Q is n lambda? Because these are equal to each other. And now we are speaking about constructive interference, and then this one is it's an integer multiple, so it's lambda n, not a fraction of that. So now there's something else I want us to look at. Okay, we shall discuss the notion of figure 8. Right. If you look at the fact that this is figure 8, but in this figure, right, we have to see figure 8 is perpendicular. OP is perpendicular to S1Q. Right, if you then say OP is perpendicular to S1Q, right, and you're able to see that indeed OP is perpendicular to S1Q. That OP is perpendicular. Okay, right, if this is the case, you have hence the angle S2, S1Q is theta. Also, if X is much bigger than D, right, so if X is much bigger than the distance, if x is much bigger than what? Than the distance. Right, much bigger than the distance itself. What x itself here is much bigger than the distance. Right, or yn. Right, S1Q is approximately perpendicular to S2P, so that we have that. Okay, let's look at the fact that S1Q is approximately perpendicular to S2P. S1Q. S1Q is perpendicular to S2P. S1Q is perpendicular to S2P. It's approximately perpendicular. It's approximately perpendicular. Okay, right. So is something you need to take note of there. And now, if this is the case, this is approximately perpendicular. If the distance is so large between x and d, then S1Q is approximately perpendicular to, right. So we are then saying S1Q is approximately perpendicular to S2P. Right. So if you look at your S1Q is approximately perpendicular to S2P. But this is true whenever x is perpendicular is very large. Okay. Right. So combining the two expressions for S2Q, we find that for bright fringes to occur for interference from a double slit, okay, we have that now. If that is approximately perpendicular, so S1Q is approximately perpendicular to S2P. We therefore have that S2Q itself is equal to D sine theta. S2Q, right? So we're then saying S2Q is then because S2Q is n lambda. So S2Q is n lambda for constructive interference. We then continue to then say, indeed, S2Q becomes D sine theta. D sine theta. Combining the two expressions for S2Q, once again, we combine these two expressions for S2Q. Right, so above we find that for bright fringes to occur for interference from a double slit, in the end, what we're able to see is therefore that S2Q equals S2Q, so that indeed D sine theta is equal to n lambda, where n itself is 0, 1, 2. If the angle theta is very small, right, if the angle theta is small, then we can then say that sine theta is approximately 10 theta for a very small angle. Sine theta is approximately 10 theta, and therefore, if you look at 10 theta is opposite of adjacent, SOHCAHTOA. So if we use SOHCAHTOA, and then we are looking at 10 theta, which is opposite of adjacent, which is opposite of adjacent, which is exactly what? In this triangle. So if we're then saying if the angle theta is very small, right, so we're looking at the case where this angle is very small, and if this angle is very small, we are saying that the sine of theta is approximately equal to 10 theta. And therefore, the 10 of theta becomes actually for a very small angle. So you have that this angle is very small. Therefore, we have that the opposite of adjacent, which is yn over x. Right. So that now we have opposite over adjacent. Substituting the above relation in equation 3 and making yn the subject. Substituting the above relation in equation 3 and making yn the subject, here, we find that the distance yn from the axis to the nth bright fringe is given by these. So now, in this case, if we replace the sine of theta, in this case, if we then have d sine theta becomes n lambda, we shall have that d, what is the sine theta? Well, I want us to discuss this theory a little bit so that we can understand this. So if we then say, obviously, in that diagram, the tan of theta is yn over x, then this is equal to n lambda. We're making yn the subject, so that if you cross multiply these things, it becomes n lambda x, n lambda x, n lambda x, and then we divide by what? By d, but this is the formula here we're getting for yn, so you can be able to get yn, and this yn is for n 0, 1, 2, and so on. Right, there will be a bright fringe on the axis. For this central fringe, the central fringe occurs when n is 0. The distance y1 to the first fringe, right above or below the axis, is this one. The distance y1 to the first fringe. So the first fringe occurs when we have that, when we have y1. Okay, then we have lambda x divided by d. Lambda x divided by d. Lambda x divided by d. So when you have y1 is lambda x divided by d. So there will be a bright fringe. So now, yeah, there will be a bright fringe on the axis. For this central fringe, n equals 0. The distance y1 to the first fringe, n equals 1, above or below the axis is y1 equals lambda x divided by d. You continue. Continue. Okay. For the second fringe, if we have lambda n is if yn, okay. So we then say, if it happens that we're talking about yn, which is n lambda x divided by d. So now for the second fringe, whenever which is the second fringe, we have y2, which is 2 lambda x, and you divide that by d. So making n equals 2, which is 2 lambda x divided by d. So this is what we're getting, etc. Hence, the spacing delta y to the bright fringes is given by what? Right, so hence the spacing delta y for the bright fringe is given by the following. Right, so the spacing, this delta y for the bright fringe is given exactly by that one. So, in other words, obviously for the spacing, you see that the first fringe is lambda x divided by d. The second fringe is 2 lambda x divided by d. Then what is delta y? Is y2 minus y1. What is y2? Is 2 lambda x divided by d, lambda x divided by d, which is lambda x divided by d. Okay, so we have the following. So we have the following. Example 5.1, interference from a double slit arrangement. 2 slits. Now, there are 2 slits, and these 2 slits are 0.5 millimeters apart, are illuminated at right angles by a parallel beam of light of wavelength 589.3 nanometers, and the interference pattern is observed on a screen that is a distance of 100 centimeters away. How far from the central fringe on the screen is the sixth bright fringe? What is the separation of the bright fringes on the screen? Okay, we discussed this solution because it's going to help us to understand this better. For bright fringes, the separation of the nth bright fringe is given by the equation 4. Thus, we have this one, which is this is a separation of the nth bright fringe, right? It is yn equals n lambda x divided by d, and this gives it because now we are asking the question: how far from the central bright fringe on the screen is the sixth bright fringe? Right. How far from the central fringe, right, on the screen is the sixth bright fringe? So which means that yn is n lambda x divided by d. So that in the end, you shall have 6 lambda x divided by, okay, so it is 6 lambda x divided by d. 6 the lambda, the wavelength, it's 589.3 nanometers times the x. So 100 meters. Okay, so now you have that you divide by d, but two slits are that distance apart. Now the distance apart of the two slits is 0.5 times 10 to the minus 3. And you have exactly the separation of the fringes is found from equation 5. Now the separation of the fringes. Now, what is the separation of the bright fringes on the screen? So the delta y is always lambda x divided by d. And the d itself can be seen as 5 times 10 to the minus 4, which is from the 0.5 millimeters. But the lambda is actually 589, which is the wavelength, 589.3 times 10 to the minus 9, because it's a nanometer. Then the x itself is actually given by what? 100 centimeters away, which is like 1.0, okay, just 1 meter from the 100 centimeters away from the screen. And therefore, that is 1.18 times 10 to the minus 3. Right. Right, so we have the following. The thin film interference. The beautiful colors often seen in a soap bubble or in a thin patch of oil on the road. Beautiful colors often seen in a soap bubble, right? Let us discuss the thin film interference. And these beautiful colors often seen in a soap bubble or in a thin patch of oil on the road also arise from an interference effect. Suppose monochromatic light falls almost normally on a parallel-sided thin film of air, thickness T, right? So suppose this monochromatic light falls normally on a parallel-sided thin film of air, thickness T, right? Between, say, two glass blocks. Right, there are two glass blocks and there is monochromatic light there. Right, that falls normally on a parallel. So it falls normally on a parallel-sided thin film of air, thickness T. Okay. Some light is reflected at AB. Okay, some light is reflected at AB, and some at CD. Some light is going to be reflected at AB. And there's this glass here. Some of it is going to be reflected, but some of it is going to be reflected at CD. Right. The light reflected from the lower boundary travels an extra distance to T for normal incidence. Right. So for normal incidence, this one that is reflected from the lower boundary is going to travel a distance to T for normal incidence. It's going to travel a distance T, but then it's going to travel another distance T there. So it's going to travel a distance 2T. Right. If 2T is a whole number of wavelengths, one might expect the two upward moving waves to be reinforced at a B, since they would be in SAP, that is strong reflected light, stronger reflected light. There is, however, a slight comparison, a complication due to the fact that if, though not at E, the light is being reflected from a more dense medium. Right, this occurs, when this occurs, the wave inverts. See figure 9, which is equivalent to it having traveled an extra half wavelength. Right, so now let us look at figure 9. In view of figure 9 here, we are looking at the thin film interference. We're looking at the shift. So now, obviously, if you are looking at glass, air, and then glass. And what then you are seeing is that if there is a wave here, right, a light wave, and this light wave, what we're able to see is traveling this way. Like this is the direction of propagation, right? So it actually it is from glass to air and then to glass again. And then obviously now, if you look at the fact that there's also now a light here that is now in this direction, that is sort of reflected. And if one looks at this as reflection now, it begins from the glass and it actually goes back to the air. Right, so, and we actually are looking exactly here as seeing no shift at all. Right, if we actually look at this and observe no shift. Right, if we're able to see a lambda over 2 shift. Okay, let's look at this one. From glass, air, and glass. And then lambda over 2 shift. And then now we obviously observe that the distance is what? Is exactly t between the two classes. And therefore, we're saying there is a lambda over 2 shift. Right, so if we're then looking at the lambda over 2 shift, and therefore, in this position here, we're seeing exactly no shift. Yet, this side, we're seeing a lambda over 2 shift. That is actually very evident. Okay, right, in this thin film interference. Thus, the condition 2t, okay, there's 2t distance. So, that is traveled when this light is reflected. For normal incidents, we said. So that's the condition that, because obviously these two glasses are a distance t apart from each other. But then you then say that 2t is n lambda. Okay. Becomes the condition of cancellation of the reflected light. If the film thickness t satisfies equation 6, there is minimum reflected light if 2t is equal to n plus half lambda. Right. So now we have 2t, which equals n plus half lambda. N equals 0, 1, 2. There is maximum reflected light. There is maximum reflected light. So that now 2t is n plus half lambda. N equals 0, 1, 2. There is maximum reflected light. For a thin liquid film rather than air between glass blocks, the cancellation condition becomes 2t equals n lambda primed, which is such that n is 0, 1, 2, and so on. 0, 1, 2, and so on. Right, for a thin liquid film, rather than air between glass blocks. Okay, now we're looking at rather than air. Okay, this is the situation of air. Right, because we said if the thin film thickness satisfies equation 6, there is a minimum reflected light. There is minimum reflected light if 2t is equal to n plus half times lambda. There is maximum reflected light. Okay, so now For a thin film, rather than air between, thin liquid between glass blocks, the cancellation condition becomes this one. So we have that 2t is n lambda primed, where n is 0, 1, 2, where lambda primed is the wavelength of the light in liquid. Lambda primed is the wavelength of the light in the liquid. Since lambda primed is related to lambda in the air, so now we then say lambda primed becomes lambda in the air divided by mu. Right? Or you can actually say this is the case. So there is mu there that is going to obviously feature there. Let's move on. Right. So we know that where lambda is the wavelength in air, okay, good. Okay, good. Right. Yeah, we're gonna jump quickly. We're almost done, but there are certain things I want to indicate here. Right, we shall move very quickly. Where lambda is the wavelength in air and mu is the refractive index of the liquid. Okay, we will actually note, because these formulas we are mentioning are the formulas we're going to use. So we need to make sure that we actually can remember the formulas, so that we then say 2t is n lambda divided by mu, or when you cross multiply, 2 mu t is n lambda for cancellation. Okay, good. Once again, I want us to make sure that we can remember the notes and quickly, and then we shall go through the activities. Okay, we can now understand the colors seen in a soap bubble. When white light falls on this film, there are some colors present whose wavelengths satisfy the cancellation condition. They are effectively removed from the reflected light, which therefore no longer looks white, but colored. Right. A similar effect can be seen in many birds, such as the hadida. Right now, this film interference of light in the layer of oil covering the feathers. We continue. Okay. Once again, I'm just trying to highlight the formulas because I'll be using them. So you need to just make sure that you can remember them quickly. Now, a thin film of petrol floats on a puddle of water. Right, so now it is a thin film of petrol, right, that falls on a puddle of water. Sunlight falls almost perpendicularly on the film and reflects into your eyes. All right, although sunlight is white, okay, being made up of all colors, white means all colors. The film appears yellowish because of destructive interference, and this eliminates the color blue, which means lambda equals 469 nanometers. If the refractive index of petrol is 1.4, and now calculate the minimum non-zero thickness of the film. Right, the cancellation of reflected light from the petrol film, we apply equation 9. So if we apply equation 9, it is this one here, and it is exactly the same as what? It is 2t equals n lambda over mu. 2t is n lambda over mu, which means that t of the minimum equals n lambda over 2 mu. Right, so now with n equals 1, right, with n equals 1, because we want to calculate the minimum non-zero thickness. Right, so the minimum non-zero thickness with n equals 1, therefore, will become exactly this, where our lambda is 469 and then 2 mu. The actual refractive index of petrol is 1.4, and this is a refractive index mu. It is 1.4, and using a calculator, we get actually 168 nanometers. Okay, let's move on quickly. I'm trying to create familiarity with the with the background knowledge, because it's all we need to solve all those problems. Now, the wedge film interference. Now, in a wedge film, the boundaries are not quite parallel, so that the film is wedged parallel. In this case, there will be various points that satisfy 2t equals n lambda. These points lie right along the lines parallel to the thin end of the wedge, giving a set of straight dark interference fringes, which represent in effect thickness contours. In between these dark regions will be bright ones, where 2t itself is equal to n plus half lambda. If the glass surfaces forming the wedge are not perfectly flat, then the interference fringes will not be perfectly straight. Thus, if one surface is known to be really plain from previous tests, the flatness of other surfaces can be tested by observing the interference pattern. So you can actually have exactly that. Okay, let us look at actually example 5.3, the wedge film interference. Two flat glass plates touch at one edge and are separated at the opposite edge by a strip of gold leaf. Air is trapped between them. When the air wedge is examined with light of wavelength 400 nanometers reflected normally from it, 19 dark interference fringes are observed. Estimate the thickness of the gold leaf in the palm, or in rather micrometers. Okay, now let's discuss the idea of cancellation here in the wedge the film interference. And obviously we know that whenever 2t equals n lambda, and we have that our n itself is 0, 1, 2, we'll see equation 6. Right, since the dark fringes, we're looking for the dark fringes are counted from 0, we must have n equals 18. Right, we must have n equals 18. Then, which means that our t, which equals n lambda divided by 2, right, from this, which is the cancellation occurs. Cancellation occurs when 2t equals this, right? 2t equals n lambda. And therefore, we know that n itself becomes exactly what? N becomes 18, right? We must have exactly n equals 18. And simultaneously, we must have that the lambda itself is 400 times 10 to the minus 9. And you divide everything by 2 according to the cancellation. And then we have exactly that. So that is something that you actually obviously need to take note of there. Right, because you have 19 dark interference fringes are observed. So that n equals exactly 18 there. Let's look at the next. Okay, briefly, because we shall be solving problems on Newton's rings, it's very important that you can actually be able to relate Newton's rings.
Sorry,
Yes, please.
is why is it 18? Why is it in 18? Sorry, I didn't get
Okay,
that.
good, right. Yeah, because we are actually looking at the fact that, first and foremost, when the air wedge is examined with light of wavelength 400 nanometers reflected normally from it, there are 19 dark interference fringes that are observed. So you need to estimate the thickness of the gold leaf in micrometers. So now we first note that always in the film interference, cancellation occurs whenever cancellation occurs, we then say 2t equals n lambda, right, for n equals those values. But now, once again, we then said, obviously, since the dark fringes are counted from 0, we must have that, because there are 19 dark fringes, but they're counted from 0. So you count from 0 and you say 0, 1, 2, 3, and you go on up to, so you'll go on up to 18, because you must count like 19 stuff. So in other words, n must be 18. Why must n be 18 if there are 19 dark interference fringes? Because they're counted from 0. So you count 19 things, but you're counting from 0. Well, it is essentially it is the dark fringes that are counted from 0. It is dark fringes that are counted from 0, not necessarily bright fringes. But at this point, you're able to see that, for example, I mean, to make it easy, what is n if you could count 2 dark fringes? Let's make it easy. Let's do 2 dark fringes, or 2 dark interference fringes. 2 dark, that would mean 0, 1, because you count from 0 the dark fringes. So you'd count 0, 1. So if you count 0, 1, what is n? N is only 1 if you count 2 of them, because you count 0 and this. So, which means that n is 1. If there are 3 dark fringes, so now if you speak about 3 dark fringes, then n is 2. Okay, right. So we move on then in view of the cancellation that occurs whenever 2t is n lambda. Right, I want us to just discuss briefly Newton's rings. The idea I'm discussing these things because we shall be solving problems about them. Now, Newton's rings, if one of the glass surfaces is spherical instead of plates, okay, here's a glass that is a glass surface that is spherical and it's not like a plate, right? Then the points where the L film thickness satisfies 2t equals n lambda lie on circles around the point of contact. That is, circular interference fringes are formed called Newton's rings. In practice, the spherical surface can be one surface of a converse lens. Right, see the laboratory manual. Right, so it is easy to show that if T is the film thickness at distance D, is the film thickness at distance D from the point of contact, and R is the radius of curvature of the lens being used, then 2RT is approximately R squared. Okay, for R relatively T. Thus, if a dark interference ring occurs, right, at radius Rn, then we then say what? We then say that 2T is just about n lambda. So, if we then look at Rn squared divided by R, it is actually exactly equal to n lambda. Yes, because if we then say 2RT is approximately R squared, we can divide by R squared over R. And then this is 2T. So 2T is n lambda. 2T is n lambda. Okay, if 2T is n lambda, then means that R squared divided by lambda is n lambda. Which means, therefore, you have Rn squared, which is a n lambda R. Okay, which gives the radius of the nth dark ring. Okay, so now we'll be able to calculate the radius of the nth dark ring. The radius of the nth dark ring is given by this. So what is the radius of the nth dark ring in the Newton's rings? It is Rn squared, which is Rn lambda. Okay, right. Again, if the lens is not accurately spherical, the fringes will not be perfect circles. Hence, Newton's rings can be used for testing lens surfaces. Notice that in the case of film interference, the effects occur at the upper surface of the film, where the two upward moving sets of waves first come together, and so the fringes are said to be localized there. Right, so we have exactly this one here. The nth dark ring, the radius of the nth dark ring is given by this one here. Rn squared is equal to Rn lambda. Move on. Let us solve a problem on the Newton's rings. A convex lens is placed on on a plain glass surface. This is a plain glass surface we're talking about, and illuminated from above with red light of wavelength 670 nanometers. The interference pattern caused by the light reflected from the convex and plane surfaces of the air film consists of a dark spot at the point of contact, surrounded by bright and dark rings. The radius of the 20th dark fringe is 1.1 centimeters. Calculate the radius of the lens. So for dark rings, not counting the central spot, Rn squared is Rn lambda. Equation 10, when n equals 20, R equals 1.1 times 10 to the minus 2 meters. Hence, we have that R is equal to Rn squared divided by n lambda. So that in the end, what we're then getting here is the following. R itself is Rn squared divided by n lambda. And now, if Rn is given, now what is the radius? Right, now, the radius of the 20th, so which means n is 20, and the radius of the 20th dark fringe is 1.1, so 1.1 times 10 to the minus 2, you square it, 20th. The wavelength, 670 times 10 to the minus 9, because it's 670 nanometers. So we get this actually here. So we're able to then to calculate the radius of curvature of the lens. So the radius of curvature is given by the big R in the formula for the radius of the nth dark fringe in the Newton's rings. All right, because that is the 20th dark fringe. That is why n becomes 20. Okay, let us discuss briefly the idea of what you call the diffraction of waves. Diffraction is the spreading. Okay, now this is a diffraction refers to the spreading of waves into regions behind obstacles. What is diffraction? Diffraction is the spreading of waves into regions behind obstacles. Right, so now it occurs, for example, when sound bends around the edge of a doorway, as discussed in section 4. The effect becomes pronounced and very surprising when the gap through which the waves pass becomes narrow. When light of a single wavelength passes through a very narrow slit, not only does it spread out, we also find that it forms bands of light. The distribution of light is a diffraction pattern. The distribution of light is a diffraction pattern. The variation in the intensity of the light across a screen typically varies as shown in figure 10. The variation of the intensity of light across a screen typically varies as shown in figure 10. The intensity drops to 0 at angles theta n given by A sine theta, which equals n lambda. A sine theta n, which equals n lambda. N equals 1, 2, 3, but not 0. N equals 1, 2, 3, but not 0. Okay, I want us to discuss this notion. So we're saying the intensity drops to 0 is at angles theta n, given by A sine theta n, right, which equals n lambda. Take note of that formula there. But we're then saying when light of a single wavelength passes through a very narrow slit, not only does it spread out because the slit is too narrow, but we also find that it forms bands of light. The distribution of light is a diffraction pattern. The variation in the intensity of the light across a screen typically varies as shown in figure 10. The intensity drops to 0 at angles theta n given by A sine theta n equals n lambda. A sine theta n equals n lambda. Okay, let us look at the following. The light of wavelength lambda. The light of wavelength lambda. Okay, now let us look at the light of wavelength lambda. The slit of width A. Here is a slit. The wavelength of the light is lambda, and it goes through this particular slit, but you really can see the intensity, the central maximum. Okay, and then the secondary maxima. You see theta 2, theta 2, theta 1, theta 1, this the slit of width A, diffraction of monochromatic light passing through a narrow slit. This is a very narrow slit because it is a narrow slit, and there's diffraction of light of a single wavelength, which is called monochromatic light passing through a narrow slit. But then you'll be able to see the central maximum, and then where obviously you're going to see these central maximum relatively brighter, and then you shall see fading. Fadings are where you have the secondary maxima. But I want us to discuss equation 11 that we're going to use in the calculation. So equation 11 is a single slit diffraction equation. Result quoted without proof. Equation 11 gives the directions of the diffraction minima. The angles measured relative to the okay, we're discussing equation 11. I need to remember that equation 11 is this one, which is A sine theta n is equal to n lambda. A, the sine of theta n equals n lambda. So now the angles are measured relative to the undeviated or straight through direction. Note that light first drops to 0 at an angle sine theta 1 given by the following. So you'd have A sine theta 1, which equals lambda. Right. So we're saying, note that light first drops to 0 at an angle sine theta 1 given by the following. Right. So sine theta 1 is given by what? Right. So it's given by the following. So you're going to have that at this point, the sine of theta 1 is lambda divided by A, which means that theta 1 becomes lambda divided by A. When theta is very small, sine theta is approximately theta. Sine theta 1 becomes approximately theta for theta that is very small. If the slit width A is very small, theta 1 is very large. So if this A is very small, theta 1 is very large. Thus, a narrow slit, right, diffracts the light through a wide angle and vice versa. Right, so a narrow slit diffracts the light through a wide angle and vice versa. Quickly, example 6.1. Quickly. Right, single slit diffraction. Single slit diffraction. Single slit diffraction. Okay, let's discuss this example. So a single slit of width 0.1 millimeters is illuminated by parallel light of wavelength 600 nanometers. Diffraction bands are observed on a screen 40 centimeters from the slit. How far is the dark band from the central bright band? Okay, now we're going to look at the solution. For single slit diffraction, A sine theta n is n lambda, where n is 1, 2, 3. See equation 11. N equals 3, which means that sine theta 3 is 3 lambda divided by A. So now, obviously, for a single slit diffraction, this becomes the case. In this case, we have that because how far is the third dark band? So because n is 3 for the third dark band, then we shall have that A sine theta 3 is equal to 3 lambda for a third dark band. And then obviously we agree that the light of wavelength is 600 times 10 to the minus 9 nanometers, and the A, which is the width of the slits, is 0.1 times 10 to the minus 3, and therefore we're able to get the 1.8. But for small theta, we can use the approximation for small theta, right? For small theta, the sine of theta is approximately tangent, so that we can actually use the fact that the tangent of theta becomes a y over x, right? So I observed on a screen 40 centimeters from the slit. So at this pointer, you have that you have the y, which over 40, and therefore this is approximately 1.8 times 10 to the minus 2, because the sine of theta is approximately the tangent. This gives us y is approximately 0.72 centimeters there. Okay, I want us to discuss quickly the notion of the diffraction by a circular hole. When light of wavelength lambda passes through a small circular hole, a circular diffraction pattern is observed. Right, is formed, as illustrated in figure 11. Right, now, as illustrated in figure 11. Okay, that is the next figure. Right, now the angle theta is the angle subtended by the radius of the dark band at the center of the hole. It can be shown that theta is related to the wavelength lambda and the diameter d of the hole by the sine of theta, which is 1.22 lambda. 1.22 lambda. The intensity of the light along a line on the screen through the center of the pattern again varies as shown in figure 10. So that in the end, you have 1.22 lambda divided by d. (1.22 lambda divided by d). So, okay, now this is very important. Diffraction by circular hole. Because I'm just pausing here so that you can note this formula, because you're going to be using it. It can be shown that theta is related to the wavelength lambda and the diameter d of the hole. So the intensity of light along a line on the screen through the center of the pattern again varies as shown in figure 10. Okay, now I want us to make sure we understand this formula, because you'll be using sine theta equals 1.22 lambda over d, but when do we use it? And that is what this says. We use it when light of a single wavelength lambda passes through a small circular hole. A circular diffraction pattern is observed or is formed, illustrated in figure 11. So that now we can then say, now the angle theta is the angle subtended by the radius of the dark band at the center of the hole. It can be shown that this is the case. Sine theta is 1.22 lambda divided by d. So the sine of theta is 1.22 lambda divided by d. So that there's something called the light of wavelength lambda. Right, so the aperture of diameter d, So the light of wavelength, here's light of a single wavelength, and it passes up through this, and you're able to see the intensity. Now, the aperture of diameter d, there's an aperture of diameter d there, and it is the hole we're talking about. And now it is obviously divided by big D. It is divided by big D. Right, figure 11 now, the intensity of diffracted light through a circular aperture, right, becomes exactly this way. And we are, because it is a circular aperture, then this is going to appear as some rings, here, this will look at some rings because this one is a hole. So the light is going to form some circles there that are like concentric. Okay, I want us to discuss what we call diffraction grating because we shall be solving problems about diffraction grating. But what is diffraction grating and how does it work? Because my belief is if you understand this very well, then we're going to quickly go through the problems. Right now, a transmission diffraction grating consists of so it is a transmission diffraction grating consists of a sheet of transparent material such as glass, okay, onto which have been like ruled a large number of parallel equidistant lines of the same width. The number of rulings varies from about 400 per centimeter in some gratings to about 6,000 per centimeter in others. Okay, so we have that variance from 400 per centimeter to like 6,000 per centimeter in others. Light is transmitted through parallel slits between in between the effectively opaque scratches. The diffraction grating acts like a set of many closely spaced slits and again produces diffraction effects. Okay, so we have the following. Let's continue. The advantage of having more slits. So now, the advantage of having more slits, more light passes through. Okay, so if you have more slits, then more light passes through. These are the advantages. So more light passes through the many slits. And then now the directions in which the maxima occur are more sharply defined. The directions become more sharply defined. So when you have monochromatic light, you'll actually therefore have that because you have too many more slits, then you'd have that the light is going to spread through the slits. But also now you're going to have N0 at the central fringe. But now the schematic representation of diffraction through a diffraction grating. Okay, let's look at diffraction grating if you have monochromatic lights and you have actually more slits. All right, then you have the dark fringes. All right, and then now in view of the diffraction grating, you would have N0, and that is going to produce a bright fringe, and N1, 2, and then N1, 2 as well. And now you're going to have different values of theta, like theta 1, and then theta 2, theta 2. So you're able to observe some symmetry there. You're able to observe some symmetry in the case of what we call diffraction grating. Okay, diffraction grating itself is very important, but what are the formulas associated with diffraction grating? If the slits are spaced apart by a distance d, then it can be shown that the angles theta 1, theta 2, etc. are given by these. So we're then saying if the slits are a distance d, right, can be shown that if these are a distance d apart from each other, there's a slit and there's a slit and the distance is d, then we can then say d the sine of theta n equals n lambda, where the theta, we've already seen that it's going to be, for example, it can be theta 1, and the theta 1 displays symmetry. Theta 1 equals theta 1 and so on, so that the d is the distance there. Sine theta, sine theta n is actually therefore equal to n lambda. But it is n lambda because now we are seeing bright fringes there, so there is a pattern of constructive interference. Okay, now I want us to discuss these three formulas we shall be using, because now note that the number of slits per unit length across the grating is given. D equals 1 over n. Equation 13, for example, is the grating equation. Right, what is the grating equation? The grating equation is equation 13, which is d sine theta n equals n lambda. Right, d sine theta n equals n lambda. Right, so equation 13 is the grating equation. Notice that it gives a direction of different maxima bright bands. But D is 1/n. So now notice that where the number of slits per unit length, right? Note that where the number of slits per unit length, N, across the grating is given, then D is 1 over the number of slits per unit length. So D, what is D? D becomes the spacing between the slits. But now, if you know that the number of slits per unit length is n, then D is 1/n. Let us discuss equation 13, but also in relation to what we need to learn. Now, equation 13 is the grating equation. So, equation 13 is the grating equation. Notice that it gives the directions of different maxima bright bands. Note too that n can be 0 for a diffraction grating, n equals 0, corresponds to a straight through beam. Compare this with equation 6 for diffraction through a single slit, which gives directions of the diffraction minima where n cannot be 0. The first two diffracted beams will be observed in an angle θ1 to the left or right of the undeviated beam, right, where theta is lambda is equal to actually the d sine θ1. So if you got this, d sine θ1 becomes equal to lambda when n is 1, right? So now for the θ1, or you can then say you can make a sine θ1 the subject of the equation, getting sine θ1 is equal to lambda over d. These are called the first order beams. In this case, now first order beams mean that n is 1, and therefore dealing with the first order beams, right? Good, yeah. We shall go through the questions quickly enough. Right, okay. Right, so now the second two beams will be observed at an angle θ2. Okay, the second two beams will be observed at an angle θ2 to the left or right of the undeviated beam where sine θ2 is 2 lambda divided by d. These images are called the second order beams. So these, you have first order beams, lambda over d, and then there is 2 lambda d, which is a second order beams, because in this case n equals 2. Similarly, third and higher order beams may be observed. Okay, quickly, in a split second, we shall discuss these to create familiarity. Violet light of wavelength 400 nanometers falls normally on diffraction grating having 5,000 lines per centimeter. Calculate the angular separation between 2/3 order beams. Are 6th order beams possible? We use the grating equation d sine theta equals n lambda. Equation 13, we've seen what we call the grating equation. And then now we make d the subject, but d is 1 over n. Right, because we've already seen that at this point, the violet light of wavelength 400 nanometers falls normally on diffraction grating having 5,000 lines per centimeter. Right, so 5,000 lines per centimeter, d is 1 over n, we've seen that, so that we have the d there. Now, having obtained the d, we know that our formula is going to be at work here, where we then say, obviously, d sine theta n equals n lambda. D sine theta n is n lambda. Right, so d sine theta n equals n lambda. At this point, we can be in a position to solve for the sine theta, and we are sure, therefore, that the sine theta when n is 3, the sine of theta 3, which is just the sine of theta, is 3 lambda divided by d. So it is 3, the lambda, which is the wavelength, is 400 nanometers, and then you divide everything by the distance d, and you have got that one there. which gives theta equals 36.9 degrees. The angle between the third order beams is therefore twice theta. The angle between the third order beams is therefore twice theta, which is actually exactly 73.4. So we note that we multiply that by 2. Now, for sixth order beams, are sixth order beams possible? That is the question. Are sixth order beams possible? So for the sixth order, sine theta, for instance, becomes this. Sixth order, we actually realize that n is 6, so that we have this, which is 1.2. Right, but the sine theta is between actually -1 and 1. Sixth order beams are not possible because of that. We move on to the next question. Thus far, we have considered the action of a diffraction grating on monochromatic light only. The really important feature of the diffraction grating is, however, that it may be used to separate light consisting of a mixture of wavelengths into what you call constituent components, since n lambda is equal to the d sine theta n. Okay, quickly, I want us to discuss the notion of the red-violet grating. White light now is shown, and the schematic representation of diffraction of white light through a diffraction grating. Right, here is white light through a diffraction grating, and what we are seeing is therefore that there is grating here, and this grating has to do with several slits. But now, when that happens through the several slits, we're able to make the following observation. So there is red-violet, n equals 2. Red-violet. So the light, therefore, obviously follows the Roig beef. Right. And then you would have the red at the top, and then you have the violet at the end. And when that happens, you therefore have red-violet, n equals 2. Then there's n equals 1, red-violet. And then there's white, which is n equals 0. Then there's red-violet. Okay, red-violet. You can see, therefore, that the red-violet is actually sort of further away from the central n equals 0 of white light. Okay, so now that is the schematic representation there we've seen. It should be clear that theta n depends on lambda. Okay, therefore, if the light from a given source consists of a mixture of wavelengths, each wavelength will be deviated by a different amount. Okay, now we then say there will be first, second, and also third and higher order images for each wavelength. Okay, if white light is used, complete spectra will be observed. Okay, it's just take note of that one. Complete spectra will be observed. Right, so we are obviously moving on here to take up these questions very, very fast. Now then, if this is the case, what then are we able to say here? Right, we're able to see that if white light is used, right, if we happen to use white light, what happens? If white light is used, complete spectra will be obtained in figure 13. Complete spectra will be actually used in figure 13. Note two important differences in spectrum forming properties of a grating compared with a prism. Right, so at this point, we're able to take note of the following. We are able to take note of the following. Okay, not too important. Okay, good. Note the following important phenomena. Right, note the following important phenomena. Right, note the following important phenomena. Right, okay. Okay, we continue. Right. Okay, yeah, we are going on, please. We're going on. Right. We are going on. Right. Okay, you're right. We are going on. Okay, I'm here. We're here. We're going on. There's something that we are looking. There's something that I'm looking at. So our aim is to produce good results. So this is awesome. This is awesome. Right. So we continue. We continue. We continue. Right. If white light is used, the complete spectrum will be obtained. Right. Note two important differences in the spectrum forming properties of a grating compared with a prism. Right. So we continue. Right, a grating produces several spectra, not just one. In any of the spectra formed by grating, the red light is deviated the most. We saw that the red light is deviated the most in the Roig beef pattern. Right, in the Roig beef pattern. Um, right, right, right. For sure, for sure. Right, right. Right. We continue. We continue. Okay, we are continuing because we shall tackle these things here. We shall tackle these things here. Right. Okay, we're going on. Right. We are going on. We are going on. Right. Okay. Right. So now, in any of the spectra formed by grating, the red light is deviated the most. We saw that. To violet light the least. Red light is deviated the most. Violet the least. Violet the least. Okay, tutorial questions, interference. Let's look at A1. Let's look at A1. What is the angle of the sun above the horizon? Right, what is the angle? Right, what is the angle of the sun right above the horizon when light reflected from a lake is completely plane polarized? Take the refractive index to be exactly 1.33. Right. Take the refractive index to be exactly 1.33. Right. I want us to look at these very carefully. Right. I want us to look at these very carefully. So obviously we note a couple of things here. We note a couple of things. Okay, we are going on, please. We note a couple of things. So now, when it's completely polarized, we note therefore that the incident angle of polarization becomes the octane of 1.33, or we can say in itself becomes the tangent of IP. Right, so that itself IP is. So you're going to use a calculator. Okay. So now you're going to have octane of 1.33, and then you close, which is actually exactly 53.06. So we actually can get that it is, say, 53 degrees, approximately that. So now then you want to interested what is the angle of the sun above the horizon? Right, what is the angle? So right, what is the angle the sun's rays make with the surface of the water? So now that would actually therefore be the same as what? It would therefore be the same as therefore the angle Right. Therefore, the angle made by the rays with the surface, right, with the surface of the water in the lake, surface of the water in the lake is 90 degrees minus 53 degrees, which is 37 degrees, which is exactly 37 degrees. So what is the angle of the sun? The angle of the sun, therefore, will be exactly 37 degrees there. So it's something that you need to take note of. So obviously, pay particular attention to the interference pattern we're seeing here, and make sure that you're able to understand this question. And as a consequence, then we actually will be in a position to obviously determine the result we need there. Okay, so take note of this. Take note of that. Right. Take note of these. Exactly. We move on to the next question. Right. Why did we subtract by 90 degrees? Right. We subtract by 90 degrees because we are looking at the fact that, right, why did you subtract by 90 degrees? That's a good question. We are looking at the sun. And if obviously you are looking at the sun and what is happening in the lake, because you're going to have a situation like this. And if this is the incident light, some of it you understand is going to be reflected, and therefore incident light, and some of it will be reflected. And then now some of it will actually therefore form an angle of 90 degrees there. Right. And so we obviously understand therefore that the angle of incidence, because we're saying it is completely plane polarized. So now it means the angle of incidence and the angle of reflection will become the same. And when these are exactly the same, we'll actually therefore say that we actually obviously this angle here is equal to that angle there for completely polarized light. And as a consequence, then what we're able to see is that this angle here is an angle of 90 degrees where there is what we call refraction. Some of the light gets refracted and penetrates the water in the lake. And so as a consequence, we are saying what is the angle of the sun above the horizon when the light is reflected from the lake completely polarized? Remember that we are interested in the light. So in other words, if you actually are therefore able to see what is the size of this angle must be the same as that angle there. Right. And also, this angle, therefore, it is part of the, you want to get this angle here, but you know very well that this angle is 90 degrees. So the angle of the sun, what is the angle of the sun above the horizon? So you can look at the angle of the sun above the horizon as this equal to this. But if this is 90 degrees, then you'd have to then say from 90 degrees, subtract this part to get the angle of the sun above the horizon. We're saying the sun is somewhere there. What is its angle above the horizon? We're interested in this angle there. But to find this angle, then you need to then say 90 degrees minus the associated angle we've got, the 53. I hope that is very clear because it is 9 degrees there. So you need to then say this one is 53 degrees. From 50, we don't want the 53 degrees, but we want the angle of the sun, above the horizon. Above the horizon, what is the angle of the sun? So it's this one. So you must say the 90 degrees here minus 53. Minus 53. Any question? So it's 37 degrees. Okay, let's look at the next one. Right, let us look at the next one. So in the next question, I want us to discuss a couple of things. I want us to discuss a couple of things. Right. I want us to discuss a couple of things. Right, 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 right. So, okay, let us look at A2. A2 is a very important question. So a sugar solution concentration of 1 gram per cubic centimeter is found, right, it is found to be, right, it's found to rotate the plane of vibration of the plane polarized light. As said already, we shall dedicate a lot of time today. Okay, so the plane polarized light. So passing through it by 6.64 degrees per centimeter of length. Okay. The same light passed through a tube 10 centimeters length containing a sugar solution of unknown concentration, undergoes a rotation of its plane, right, of its plane of vibration of 8.3 degrees. Right. So the question then is, what is the concentration of the solution? Let us pause to reason this out, but to reason this very, very carefully and make sure we actually understand what is happening here. So in the notion of the sugar solution that we're dealing with, the couple of things that we need to take into consideration. Okay, so I want us to discuss this very, very carefully. Think about the things we need to discuss this, and make sure, therefore, that we understand precisely what is to be done. Okay, right. So we are beginning our solution to this, but the couple of equations that we have learned, and now, as a consequence, let us think about these very, very carefully. Right, very, very carefully. Okay, there are formulas that we have learned, and I want us to use those formulas we have learned. Let us pay particular attention to the fact that the results we need to use, we've already discussed the equations we need to use. So we shall bring them to the surface. There's something we call the optical activity. Right, I'll discuss what you call the optical activity. So we already know that theta becomes the concentration Cl. Now, this one is called the specific rotation. Specific rotation. When theta is the amount of rotation. The amount of rotation. The amount of rotation. And then I want us also to discuss the following. Right. So we're then saying, what is the concentration of the solution? So obviously, a couple of things you need to take into account. It is that to find the concentration of the solution, the concentration C So now I'm just speaking about the symbols. The amount of rotation, the specific rotation is the theta in the square brackets. The theta without brackets is the amount of rotation, and C itself becomes the concentration. C denotes the concentration. And then L refers to the path length. All right, it refers to the path length. So that now to find the concentration of the solution, we need C. So if theta is equal to the specific rotation, or the amount of rotation is a specific rotation, the concentration multiplied by the path length, we would find the concentration. So you have this one, L, this one, L, so that in the end, you'd have the concentration is theta divided by the specific rotation, L. So I want us to look at this because the sugar solution, right, of concentration 1 gram per cubic centimeter. That is the concentration. Right. It's found to rotate the plane of vibration of polarized light passing through it by 6.64 degrees per centimeter. Okay. Let us pause to reason what this means here. All right. So if you look at the fact that you are looking at a sugar solution of concentration Z, so we have been given concentration found to rotate the plane of vibration of polarized light through it by this. Right. So this one is theta. So look, theta is 6.64 degrees. So the concentration itself is 1 gram per centimeter per cubic centimeter. One gram per cubic centimeter. Okay. It's found to rotate the plane of vibration of polarized light passing through it by that per centimeter. Okay, per centimeter. So just take note of that. Right. And this is the case per centimeter. Right, per centimeter. Okay, of length. The same light. So now, if you have been given these two quantities, and it is about the light that is being given. So you have been given theta, you have been given the concentration, and now at this point, you have two unknowns in this particular equation. But the same light passed through a tube. So in other words, I mean, what we're able to get at this point is the following. Right, it's the following. So you can do a quick substitution here and then say, what is your theta? It is 6.64 degrees. So it is this one. The concentration is actually 1 gram per cubic centimeter. And then you also have L. The same light passed through a tube. Okay. 10 centimeters length, containing a sugar solution of unknown concentration, undergoes a rotation of its plane vibration of this. Right, so same thing. Now you have another case, and then now it is passed through a tube of length that. So, okay, I want us to analyze this and then say the tube is of length 10 centimeters. And then, right, containing a sugar solution of unknown concentration undergoes a rotation of its plane vibration of this one. So you are speaking about the plane polarized light. So, which is 8.30, 8.30 degrees. Right. So what is the concentration of the solution? That's actually what we want here. So obviously at this point, you would then say in the second situation, you have theta is equal to this one, CL, until you have 8.30 theta, and then the concentration times 10, like this. And so what actually can we be able to get? So what is we want a concentration. So you can say, because the same light, then the concentration is given by 8.30. You divide by what? By theta times 10. Okay. So that in the end, so now you have this. You have this. You have exactly that. Right, 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 right. So now, if this is the case, you are interested in finding the concentration, but what exactly will be the concentration? So you need to obviously now think about the specific rotation. What would the specific rotation be? Because you have a sugar solution of concentration 1 gram per cubic centimeter is found to rotate the plane of vibration of plane polarized light passing through it by 6.64 degrees per centimeter of length. Okay, so it does this per centimeter of length. So if it rotates it, so this becomes the rotation when the length is 1 centimeter. When the length is 1 centimeter. So you can put 1 centimeter here. Like this. Meaning, therefore, this is 1 by 1. So, which means that you can take this one to be exactly the following. So 8.30 divided by, so this one is going to be 1 times 1 is 1 there, giving us the 6.64 degrees times 10. So let's use a calculator here. You'd have to then say, using a calculator, right, you then get the 8.30. Okay, let's do this one. 8.30. Once again, today we're available the whole day, so you can communicate. You can communicate. So we're available the whole day today. You can communicate and let us know. Right. We are estimating the concentration to be 0.125. 0.125 grams per cubic centimeter. So that will be the concentration. We estimate the concentration to be exactly that one, 0.125 per cubic um per cubic centimeter. Okay, so think about this. Okay, think about this and make sure that you understand this. Right, 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 right. So, any question on this? Any question on this? Any question on this? Right, so that is a small little problem.
Sorry.
Yes, please.
So this is the way that you can identify whether uh the degrees that you've given have been given is the specific rotation and the amount of rotation. So you have to use this procedure in order to find out.
Yes, yes, most definitely. Because so let me see what you've got. Okay, because that is done exactly that. So okay, there are a couple of ways. There's something I want to also say about this. There's something I want to also say about this one because if that is 52, okay, just there's something I want to say. If you do something I want to check here, you do, for instance, if I do 60, and then because I mean we can use degrees or radians. So 52.3, for example, times 10. Right. That is how it should be done. So those degrees you can actually do them exactly like this. Okay, I was just obviously also testing this method against the use of radians as angles because angles can either be determined in degrees or radians, as we know. But this would be one way to do this particular question, and it gives us a very reasonable concentration. As a matter of fact, here, and we are able to see exactly what this gives us is the answer. But yeah, this would be a method that we can actually be in a position to use. We move on to the next question. We move on to the next question. I said already we're available for the whole day, so it will be up, excuse me, up to you to let us know when you're going to be free again. Okay. So now, if you're dealing with the two sources are emitting, right? Okay, two sources. All right. Let me speak. Yeah. Okay. Yeah. Hello, my dear. Yeah. I'm in class. I'll let you know when I'm done with my class very soon. Okay, my dear. Yeah, I'm in class. I'm finishing my class now. Okay. Thanks, my dear. Right. Good. So you're dealing with two sources. Now, these two sources are emitting identical waves that have a wavelength of 0.44 meters. Determine whether constructive or destructive interference occurs at a point whose distances at two sources are as follows. Okay, yeah, so you have this, you have this, you have this. Okay, let us look at this and reason this together. Let us look at these and reason these together. So if you're talking about two sources, and these two sources, what are they doing? Are emitting identical waves that have a wavelength of 0.44 meters. So you continue to then say, at this point, you would have exactly the following. Okay, let us look at these and reason these very, very carefully. Okay. So, yeah, we are looking at this question, and it's a very interesting one. We pause to reason these carefully, like we did, like we have done the previous. So now, this is going to be A3. I said already, we are here. We are here. So now we are here. So two sources are emitting identical waves that have a wavelength of 0.44 meters. Determine whether constructive interference takes place or not. Determine whether constructive interference takes place or not. Okay. Right. Let us look at these, but very, very carefully. Right. At a point whose distances are right from the two sources are as follows. So now in part A, if the distances are, for instance, from the two sources, 1.32 meters, 3.08 meters. Okay. So now you would actually therefore analyze these as follows. Let's look at how we're going to analyze this particular question very, very carefully. Um, so now, okay, good. We are continuing. We are continuing. Okay. Now, this is a very, very interesting question where we are then saying, we are then saying, we are then saying, we are then saying, okay, we are looking at this very carefully. We have two sources are emitting identical waves. Okay, good. So it's like we've seen this before, and these are emitting identical waves that have wavelength 0.4. Okay, we are looking at these and so we're going to relate these to a scenario. We're going to relate this to a scenario. This is a scenario we looked at, and we're going to discuss this here. So this is like Young's double slit. Young's, because there are two sources, it's double. Young's double slit experiment. Right, so these two sources are emitting identical waves that have wavelength of that much. So we know that either way, the wavelength is 0.44 meters. Determine whether constructive or destructive interference occurs at a point whose distances from the two sources are as follows. So you have these distances. Now, there's a point. There's a point P. And then you have the sources, of course. Let us call these source 1. And then we're going to call these source 2. And then if we're then saying, okay, this one is the distance. If the distance here, for example, is 1.32 meters, and then there is also a bigger distance, that you need to take into account. So there is a distance of the following, which is source 2, and then if this one is like further away because it's 3.08 meters, okay. But we agree that these have the same wavelength, but those distances are different. So now, if this is the case, we are asking the question, determine whether constructive or destructive interference occur at the point whose distances are those. Okay, so now to actually obviously answer this question in full, you have those distances, and those distances here are the following. Okay, we're going to analyze those distances and the significance of those distances. Right. Okay. Now, if we then use the formulas we know, Yn Yn which is n lambda x divided by d. So now in the end, then you'd have the following. Right. Okay. Right. So we're gonna do part A first, and then we're gonna do part B next. Right. Okay, there's more I want to say about this particular question here. Right. So if you are to look at it, for instance, from the Y1 would be lambda x over d. The wavelength is 0.44. Okay, 0.44 meters. Okay, and then we're using also the distance. So there are a couple of distances, like there's 1.32. Yeah, it's one of the distances, because this distance is to call them x. So there's like x1, x2. Then you're gonna have that is the distance. And then you would have d. Okay, the two sources are emitting identical waves. They have a wavelength of this. And obviously, what don't we know? Because when we're told that determine whether constructive or destructive interference occurs at a point whose distances from the two sources are as follows. Okay, there's a point whose distances from the two sources are as follows. But we don't know the distance between, we don't know the distance d between those slits, or between those sources. We don't know the distance d. But we just know that the point P is some distance away from that. Okay, so this creates, for instance, for the right, the distance y1 to the, so we can be able to get the first fringe. And the first fringe when n is 1 would be this one. So now, in other words, we take this when n is 1. Right, so agree that here we can then say if n is 1. Okay, if n is 1, then we have this. Right, right. So you would then obviously be in a position to get this. But now, simultaneously, you can also get another y value. Right, you can be able to get another y value because you still know that the distance x is 3.08 meters. So if the distance x is 3.08 meters, it is our x there, for example. So you can then also be in a position to observe the same thing. That if this is the case, okay, there's more I actually want to say about this particular question because it's not. So you can look at the fact that y1 for the source 2 would be lambda x. What is the lambda? Okay, so which is 3.08. So now, okay, for the 3.08, for instance, we will be able to see that this would be the case for the y1. Okay, we'll see that it's going to be exactly the case there. And there's more I want to highlight at this point. Right, there's more I want to highlight at this point. Right. There's more I want to say at this point. Okay. And in the same way, what would y2 be here? It's going to be 2 lambda x divided by d, which should be 2 times 0.44, 1.32 divided by d. Okay. But in the same way, as much as we've got y1 here, there's going to be a y2, which is going to be, according to this formula, 2 lambda x over d. 2, the wavelength is 0.44, and then 3.08 for the one that is further away, and then you have the distance d between them. Okay, so think about this. Okay, so now the couple of things then you need to take into account. Now the question is, what would the spacing d be, for example? What would the spacing d be, for example, here? Right. Right. Now, this is sort of the setup, but now we need to analyze the systems of equations and to be able to arrive at a conclusion that is best for this. So the question then is, if this is the case, what would the spacing of the bright fringes be? What would the spacing of the bright fringes be? Right, and I want us to discuss the spacing of the bright fringes. Right. So now we need to remember something. It is the fact that constructive interference so you have theta. You have S1. So that in the end, you have P. So now, you'd have this. Okay, the distance. And then we then say, okay, these two sources are in different positions. And so we know that if we say S2P minus S1P equals n lambda, and then we then say constructive interference occurs when which is S2P so which means that you have S2P minus S1P so now which means that S2P minus S1P is lambda x because these are like those two differences. Okay, these are like those two differences. Okay. So now if we then are then saying if the wavelength is this, and we then say we subtract these two. Let's look at part A. I think it might actually be a much easier way, so we use this result. So if we then say whether the constructive or destructive interference takes place at a point whose distances from the two sources are as follows. What this guy might have meant is that we just use this formula, and then you're going to say S2P minus S1P must be n lambda. So you have 3.08 meters minus 1.32 meters is actually equal to n 0.44. And therefore, this n must be an integer. So, but you can divide this one. This one is in meters. Okay, so we're going to take a calculator. So we're going to take like 3.08 minus 1.32. Okay, so 3.08 minus 1.32, you get like 1.76. 1.76. Let us do all this. Then you'll come here and then take 2.67 or like 3.33 minus 2.67. And then we have 0.66. 0.66. Okay, just to do these differences. And then we're going to do here 2.20 and 3.75. 3.75 minus 2.20. 1.55. 1.55. Then we're going to do 4.18. So if you have 4.18 minus 1.1, 3.08. Okay, if these are sort of the distances, but you must do A, B, C, then D. Okay? So now we're going to do these differences, which are S2P minus S1P, which is N lambda. So if you subtract these, you'd have, okay, let us start with A. In A, we got 1.76. In B, we got what? 0.66. In C, we got what? 1.55. In D, we got 3.08. Right. You have the following. So now, then you'd have to then say, we want to determine N. We must find N. So N is S2P minus S1P divided by lambda. So you must divide this one by lambda, this one by lambda, all of them by lambda. And then lambda is what? Wavelength is 0.44. So let's divide. So we divide the difference by lambda, and then it's going to give us an integer. This N must be an integer. If the N is an integer, then we have constructive interference. Okay, so let us do that. So that is the easiest way to do the question. So you're going to take 1.76. You divide by 0.44. Good. We get a 4. Constructive. Then you're going to do the next one. So A is constructive. Then let's do B. 0.66. You divide by 0.44 wavelength. 1.5 destructive. Then C. You're going to do 1.55. You divide by the wavelength. The wavelength is up there, which is 0.44. Okay, yeah, because we'll also continue later. 1.55. You divide by 0.44. We have 3.5. Now, 3.5 is destructive because it must be an integer. And then we have 3.08. You divide by 7, constructive. So in other words, you want to know this one. So this one is constructive. This one is destructive. This one is destructive. Okay, we say constructive interference, destructive interference, destructive interference, destructive interference. So then you'd have like the two constructives, like A and D are constructive, and then B and C are destructive. So I think that we're going to take a break, and then we shall come back again. We're going to take a break, and then we'll come back again because we've done A3. So now you will let us know where you're free during the day, and then we shall do the other questions. We shall just spend time discussing them and look at how they need to be solved. But this one is Young's double slit because it's two sources that are emitting identical waves. It's monochromatic lights, identical waves, same wavelength. Young's double slit experiment. Okay, so yeah, we've solved this one. Any question on this one, A3? But yeah, during the day, we're free, we're available throughout. So we're going to make this recording available, but we shall do more questions even later on. Okay. And then we shall practice, discuss. Practice, discuss. But we have to do questions from each group because, you know, there are different groups of these, like your your interference patterns, your diffraction grating, you name it. So we have to discuss the questions from each group. Okay. So any question? Please, yeah. So we keep in touch, please. Throughout the day, you are available. So let us know to say, at this time, you're available during the day, 24/7. Then we can continue with the rest of the other questions, like A4 and the rest of the others. Right. From us right now, it's also I'm having this discussion until we hear from you during the day. We shall send the recording in the next couple of minutes, this one. But thank you so much for now. Take care and goodbye. Right. Goodbye for now.